So last time we made this Arena Allocator and used it to get Lua to allocate all of its memory from a little piece of memory that we put on the stack, which is really good. And this allocator just burned through all the memory and then deallocated at the end in one big lump. And that's all great, but I did add this comment after the video, which is this allocator does not align memory correctly. So we just allocated memory and allocated and allocated, and we didn't care about how the alignment was. Now, if you don't know what memory alignment is or why it's important, then it's well, I'll explain it now, because the problem is that I was looking on YouTube about videos about memory alignment, and there's a lot of videos that explain what memory alignment is, but they don't explain why you need it. So that was really the kind of crux of the whole thing, which is the program we had before actually misaligned a lot of memory that we were using, or it might have misaligned it, we're not quite sure. But the program worked fine, it didn't crash and nothing happened. So the question is that why should we bother trying to align pieces of memory with certain addresses? And the answer is because of the way the computers work, and depending on what happens with the alignment, a few things might happen. Like, one of the things that might happen is it will be slower, which is probably what's happening in our case, and it's a little bit slower to access certain things, so the program carries on working fine. The second thing is it might break threading. So if you've got two threads accessing a piece of memory, some things might go wrong, and that'll be one of the hardest things to debug, because that'll just happen every now and again and you won't know why, and it'll happen in different places. It may or may not break your threading, and in our case we weren't doing any threading, so we wouldn't have noticed that. And the third case is if you're using certain instructions on the CPU, like SIMD instructions, for instance. Some of those require a certain memory alignment, which if you haven't provided that memory alignment correctly, it will just crash. So three things are going to happen. In our case, we didn't do any SIMD, we're not doing any threading, and we didn't notice the slowdown. So in our case, the memory alignment just wasn't an issue. So depending on your platform, not having memory alignment could be the correct thing to do, but usually it's not. And the problem comes from the way computers access memory. So if I just draw a little diagram of a block of memory, I'm drawing with the mouse, so this is going to be really bad. So let's imagine this is a little block of memory, and each one of these little squares is a byte of memory. So this is a tiny block, and this just goes on forever. So we've got, block 0 here, block 1, byte 1, sorry, byte 0, byte 1, byte 2. And what happens when the computer, say, wants to store a byte of memory? So let's say it's storing bytes. So it'll come along and say, I want to store 1 byte, I'll store it here, and there's that 1 byte filled. And then it says, I want to store another byte, I'll store it here. And that's all fine, but then what happens if it wants to come along and store, say, a float? Now, a float is 4 bytes, depending on your platform, but on most platforms it's 4 bytes. So then the computer comes along and says, oh, I want to allocate space for a byte. Where am I going to put it? Now, in our current Arena allocator, if we'd have allocated 1 byte and then 1 byte, and then we wanted to do 4 bytes, it would just stick it right next to the others. So it would just put the 4 bytes across here. And then maybe we'd allocate, what was my color? Was it that one? I don't know. And then maybe another byte goes in there, and then maybe we do another, 4 bytes going across there. And you might think, well, what's the problem with that? That's not a big deal. Well, depending on your platform, it might not be a big deal. But what you'll generally find is that hardware will, when it accesses a little piece of memory like this first byte, it's not actually just accessing that first byte, it's accessing like a whole block of memory, and it's got like the hardware thread that's doing that access has got exclusive access to this little block. Now, I don't know what the block size is, it could be anything, but let's just imagine that in this hardware case, it's every 4 bytes. So there would be a block like here, and then 1, 2, 3, 4, and then there's a block there. So we've got a block here, we've got another block. So storing the memory like this is actually fine. These bytes are all stored correctly. This float is stored correctly, and this X is stored correctly. This other byte is stored correctly. They're all still there in memory, but as you can see, they're not aligned inside these like 4 byte boundaries that we've set up. So what's actually going to happen is the CPU comes along, and let's say we want to read this float out of memory. What it actually does is it comes along and it says, okay, the start of the float's here and it ends here. So what I'm going to have to do is read out this piece of this block, which I lock, and I'm going to have to read out this piece of this block as well, which I also lock. So it's going to read and, like, so let's say you were writing this float, it's going to read and write in these two separate pieces of memory. So the problem with this is it's actually 2 writes to do this little 4-byte block. Now, the problem with that is it's slower. We actually, when we accessed this part of the float, this whole piece got accessed and these got locked out as well. And then when we accessed that other part, it accessed that piece and this whole piece got accessed as well. So we locked all these 8 bytes, even though we were only actually interested in these 4. And the problem is it happened in 2 sections. So it's slower because we've got the CPU to go across this like memory boundary. And it also, from a threading point of view, the strange thing that can happen is these 2 bytes here can be written first, and then these 2 can be written second, or vice versa. So if there does happen to be another thread reading this memory at the same time, it can see half a float. So it can just see corrupted data. So memory alignment from that point of view is slower, but then from a threading point of view, you can just get undefined behavior. And then there is a third problem, which is that some operations in the CPU just require it to be aligned correctly. So there might be some SIMD operations that require you to be aligned on 16-byte boundaries, for instance. And this in this case just won't work. And the CPU will just crash at that point. It just won't know what to do. So that's the reason why misaligned memory is bad. So what we really should have done here is, in our case, is we would have allocated the first byte, allocated the second byte, and then our float should have started there and it should have been aligned in this section here. So it would have been aligned in this whole 4-byte boundary. But that's not what we did, because each time we asked for a piece of memory from our pool, we just gave it the next pointer and the next pointer and so on and so on. And our memory alignment was just all over the place. So that's really the problem. That's the explanation of the problem. And also another problem we've got is in our Lua implementation is that Lua isn't telling us what this thing it's allocating needs to be aligned for. So we have no idea of what the alignment actually is, what the alignment requirements are for this particular piece of memory that it wants. So that's a bit of a problem. What we can do is just we can just make an assumption in our program that we don't need to align anything bigger than 8 bytes, because that might be the size of our pointer, for instance. And we're not going to use SIMD, so we're not aligning anything to 16. So we'll make the assumption that everything needs to be aligned to 8 bytes. And keep in mind that if we align to 8, then something that needs to be aligned to 4 is also aligned to 8. Something that needs to be aligned to 2 is also aligned to 8. And something that needs to be aligned to 1 is also aligned to 8. So 8-byte alignment will work for everything for 8 and below. So that is all good. So I think that's what we'll do. We'll just implement making sure these things are 8-byte aligned. First thing we're going to do though is I'm actually just going to move this allocator into its own separate file, because we're going to use this again and again in lots of different places. We'll use it in all our Lua states from now on. So I'll just move it into its own file, and then we can just include it and use it again and again. So I'll do that like this. This is my CMake project, Arena Allocator. So just do that, and it should change the Visual Studio project for us. So we should have Arena Allocator. There it is. So we've just got a new blank header file for this, where I'm going to put the allocator. So I'm going to take that out. Let's go full screen. Let's take that out of just inlined in our main method. Let's take that out of there, and we'll stick it in here. So let's just fix, make a copy of this as well, because that was our old. So we're going to do an aligned memory allocation. We'll include Arena Allocator. That actually just worked, which is surprising. That these includes from up here are probably getting included down there. Let's include that first so we know what its dependencies are. Yeah, so this needs an include of assert. It needs assert. What else does it need? It needs printf, which is the standard IO. What else does it need? Memcopy, where's that coming from? Is that coming from new? It's not coming from that. It's probably coming from string, is it? Maybe? Or maybe it's coming from the Lua include. No, it's coming from string. We don't actually need string, but I'm including it there. I don't know what the include is for memcopy. We can find that out later. And it's interesting to note that we don't actually have to include Lua in this allocator, even though this is an allocator for Lua. Because if you look, our allocation doesn't even require anything to do with Lua at all. It's just all like pointers and stuff. So this is completely independent of Lua, this allocator. And that the good part about that is we can test it independently as well. We could write unit tests for that and test that completely independently of any Lua state if we needed to. And that's probably what you should do in the case that you're actually writing one of these for realsies. Let's just check this still runs. So it's still running, it's still printing out all our allocations. And what I want to do to demonstrate the point with this particular problem is we'll create a I need more room because we've got such a big font. We'll basically create a new user. We'll do a new user data. New user data. And we'll make it from, I'm going to make a struct called thing. And I'll just put an X and a Y in it. I've been doing this before. Well, let's make them floats just to make it different to any of the other things we've ever done. Not that it makes any difference. And let's say this thing needs, let's just, I think this is how you do this in C++11. That's just specifying that this struct has to have an 8-byte alignment. So we're just explicitly stating it there, that this thing needs to be aligned to 8. And we'll create the user data. We need a size of thing, and it's going to be a pointer to a thing. And that's all good. So that should, oh, it's not referenced, but we've made our thing. But the problem with this is that although we're passing in, like we're using kind of like structures and stuff like that, Lua doesn't actually know what this thing is, because all we did is we told it the size and it gave us back a void star. So it doesn't know about this alignment that we specified. It's got no idea. So what we should really do is assert that the alignment of this thing is actually correct, which would be, we do align of, we can ask for the alignment of a thing. If I could type correctly, we could. So if I mod it with that, the remainder should be 0 if we're aligned correctly. Are we aligned? The question is, when this thing got allocated, did it get aligned to an 8-byte boundary? I don't think that's going to compile because it doesn't know how to do it on this T. We're going to have to cast it to a number. So we're going to cast it to a uint pointer T. That's basically just turning the pointer into a number so that we can do this, what is basically a math operation on it. But yeah, we're just making sure that we can get that pointer and turn it into a number that's big enough to hold the pointer. So let's just see what we get. So it failed. So what's actually happening is our thing is not aligned to 8 bytes. It's a miserable failure. So our thing may work correctly. I mean, it depends on how critical this alignment is. If we were going to do some SIMD on this or something like that, it would probably crash the program. So that's really bad. And of course, the problem with Lua is that when we did new user data, we didn't specify the alignment here. I mean, really, what we should have done, or what I think maybe Lua should be doing this, and it's not, is that when you create one of these, really, I want to pass it the alignment so that it knows how to align this memory, but Lua doesn't support that. So we're just going to go with what we've got, and we're going to align everything to 8 bytes. But at least we've got a test case here. I mean, this may not crash every single time, but it seems pretty consistent here that we're not aligning this memory to 8. So we're going to align everything to 8, and that's going to be our solution. And the way to do that is, it's not the most complicated thing in the world. All we're going to do is every time we allocate here, this is the current is the pointer to the next piece of memory we're going to allocate. We're just going to align this up to the next 8 byte boundary. So let's just specify in here. Let's specify that we could pass this in the alignment, but don't want to align to 9. So we're going to specify here as just a static, like a total constant, that everything's going to be aligned to 8. So every time we allocate some memory, whether it's 1 byte, 2 bytes, 4 bytes, 8 bytes, 16 bytes, it's going to be aligned on an 8 byte boundary, and that's what we want. So all we have to do here is make sure that just before we use the current pointer, that we align it up, and when I say up, we make it bigger to the next 8 byte boundary. And the reason we have to make it bigger is we're increasing each time we allocate, we chip off a bit at the end of this block. And if we make the alignment go backwards, as in we go to an earlier pointer, we might give someone memory that we've already allocated. So we have to align to the next 8 byte boundary, and it has to be the same as or bigger than the current pointer. And the way we do that is if you've never done this before, you take the pointer you've got, you add on the alignment -1. So that takes us up, but we're still not aligned, so we're going up. And then we mask off the alignment -1. So the inverse of alignment -1, and that just takes us back down to the 8 byte boundary. You might want to spend some time, if you've never done that before, spend some time just studying that and see why that works. But that's basically aligning, but it's aligning up to the next 8 byte boundary. Again, for the same reason as before, this won't compile because we're turning this pointer into numbers to do some stuff on it. So let's just convert it to the unit pointer t, and then we have to convert it back to a character pointer. So let's just see if we can get that whole line on the screen. So yeah, you might want to spend some time working out why this works. Does it compile correctly? What have I done wrong here? Illegal what? Type has... Oh, if I'm missing a bracket here, I think I'm missing a bracket. Yep, missing a bracket. That didn't make any sense. No. I'm missing something here. Missing another bracket. Missing 2 brackets. How many am I missing here? That's that one. That's that one. Is it another one? No? Something very wrong here. Got that one. I just want brackets around all that. Yeah, I don't know what I just did wrong before, but I did something wrong there. So there we go. So apart from all the hideous brackets and casting, you could make that more readable if you want to put it in a function or do these alignment -1s in another variable. That should align us up to the next 8-byte boundary. And then we do that before we assert for the see if we've run out of memory, because doing that alignment up might actually take us outside of the current memory that we've got allocated. So let's see if that works. Well, no crashes. So we've successfully aligned, when we allocated that user data, we successfully aligned our thing to T. The only other problem is everything's going to be aligned to 8 now, but that's maybe one of the things we're going to have to work with. And it's possible that might be something that you want. You might want to align to 16 or whatever, or you might want to align to less. But in our case, that's going to align everything that we allocate out of this pool to more, and it's going to waste a few bytes at the end, but we're going to have to do that to get this to work correctly. So the actual fix for this in the end was just one line, which was just that. But that solved our memory alignment issue. So this is now correctly, I would say this is correct, this allocator, it works correctly. Whereas before it might have worked correctly, but now I think it does. So that's the memory alignment covered. So next time we'll probably look at getting this to reclaim some memory, or getting it to allocate more memory if it runs out of this pool. So we'll do that next time.